Hello class, this is the sixth tutorial on RC circuits, and once we get done with this tutorial we're halfway home. There are only 12 tutorials in the semester, so let me just share my... Okay, now you should be seeing the tutorial handout that was in that packet that you bought from the bookstore and for $4.50. Uh, Throughout this tutorial, when you are asked to predict the behavior of a circuit, do so before setting up the circuit. We're going to use our model to see if we can predict what's going on. Now, I just want to point out that even though the title of this tutorial is RC circuits, and we're going to be playing with RC circuits, where R means resistor, the bulb, C means capacitance, the capacitor. Even though we're playing with RC circuits, this tutorial really is about the voltage model and helping you to um, get more familiar with your voltage model. So let's go ahead. Simple RC circuit. A capacitor is connected to a battery, a bulb, and a switch as shown. Assume that the switch has been closed for a long, long time. Now we saw this in lecture. We know what happens. When you first close the switch, that bulb is bright. It's as bright as that single bulb circuit. And then over time, as the capacitor fills, as the capacitor gets charged up, the bulb gets dimmer and dimmer and dimmer until it goes dark. So we know that if we leave that switch closed a long time, the bulb is dark. Predict how the voltage, again, I did not publish this one here. Predict how the voltage difference across the battery compares to the voltage difference across the capacitor plates and to the voltage difference across the bulb. Well, we know that since the bulb is dark, it has a voltage difference of 0. And I know that along any path from one side of the battery to the other, the voltage drops have to equal the voltage rise of the battery. So that means that the voltage across the battery has to equal the voltage across the capacitor. Now, we're asked to describe the distribution of charge on the capacitor plates. Well, since this is the positive terminal of the battery and this is the negative terminal of the battery, this plate here closest to the positive terminal will be charged positively, and this plate near the negative terminal will be charged negatively. Now, the way the battery does that is that it steals electrons from this plate and brings them all the way around through the bulb to the other plate. So for every electron that ends up on this bottom plate, we have a naked proton left behind on the top plate. And so we're going to have a distribution of charge like that. Recall the relationship between the charge on a capacitor and the voltage difference across the capacitor. Use this relationship to describe how you could use a voltmeter to find the charge stored on the capacitor. You remember capacitance is defined as the charge stored on one plate, the positive plate, divided by the voltage difference between the terminals on the capacitor. Now, I can use that relationship to solve for the charge that's stored in the capacitor by just multiplying both sides by the change in voltage across the capacitance. And so what I get is that the charge stored is just the capacitance times the voltage across the terminals. And that makes sense because capacitance is how much charge can be stored for 1 volt. If I've got 12 volts, I just multiply that by 12 and get the total charge. Now, we would like to check our predictions here. And so I'm going to, um, now I'm going to switch cameras here, and I want to not switch back and forth. Once we check our predictions, we're going to remove the capacitor and the bulb from the circuit, and then we're going to predict the voltage difference across the bulb, the voltage difference across the capacitor, while these elements are disconnected from the circuit and from each other. And then we'll check that prediction. Okay, now we go here, we change the camera. Oh, dang. How do I keep doing that? There we go. Okay, figured that out. Okay, this has been uh, connected for a long, long time, and we're going to use this voltmeter to first of all measure the voltage across the bulb. And as predicted, that is 0, maybe even -0. Okay, whatever that means. And then I'm going to measure the voltage across the battery. And there I get pretty close to 3 volts, 2.98 volts, 2 point, yeah, 2.99, something like that. Okay, and now I'm going to measure the voltage across the capacitor, and what I get is 2.97, pretty much the same as the battery. Well, now we're asked to disconnect these from each other. And if we, well, first we have to predict what we think we're going to measure across this bulb that's disconnected. I predict that we're going to read 0. That's just not an element that we've ever seen voltage across unless it's in a circuit. And we get 0. But we know that once we charge up a capacitor, it acts like a battery. Okay. And so I expect that this capacitor will still have 3 volts across it. And when we measure that, we get pretty close to 3 volts. Okay. Now we're going to go back to our other camera. Okay. We predict that the voltage difference across the bulb is still 0, and the voltage across the capacitor is still around 3 volts. And we checked our prediction. Now, predict whether the voltage difference across the capacitor will increase, decrease, or remain the same if a wire is connected from ground to one or the other of the terminals of the capacitor. Now, I know the answer, so I would like you to predict what you think is going on. I'll draw a picture. We've got this capacitor charged up with positive charge on one plate and negative charge on the other plate. And if we take this lead here and hook it to something big and metal to ground it, um, ideally we would go find a sink that had a pipe that was going down into the earth. The earth acts like a huge metal ball. Um, are all of these electrons going to escape to get on the big metal object? Um, let's let's find out. Okay. So after that, we're going to devise and carry out a method to reduce the voltage difference across the capacitor to zero. In other words, discharging it. So that we don't have to switch back and forth so often. Okay, so I'm going to take this capacitor that's charged up, and I'm going to just, oops, boy, it's magnetized there. I'm just going to touch, I'm just going to touch one of these leads to the metal desk. Okay, and then we're going to measure the voltage across that. And lo and behold, it's still got volts across it. Now it seems like this particular capacitor has a little bit of a bleeding circuit in there so that when it's on the shelves for a long time, it slowly discharges itself. But if we want to discharge a capacitor um, quickly, we could just touch these two leads together and all the electrons would race back to where they came from and discharge the capacitor. Now, with many capacitors, discharging it very quickly like that can damage the capacitor. And so it's better if we discharge the capacitor through some resistance like this bulb. And what we see is that the bulb gets bright and uh, that then as time goes on, the bulb gets dimmer and dimmer and dimmer and then goes out. Okay, we'll switch cameras again. Okay, so our method was to hook the two leads of the capacitor to a bulb. The capacitor in part A is said to be charged by the battery. Does the capacitor have a net charge after being connected to the battery? And the answer there is no. Um, we have a positive Q on one plate and a negative Q on the other. And so the net charge is always going to be zero. In light of your answer above, what is meant by the charge on a capacitor? Well, it's only the electrons that are free to race through the wires to light up a bulb or to run a fan, to do some sort of useful work. And so it's only the charge on one of the plates that is useful. Now, we use the charge on the positive plate just to get rid of a minus sign and to undo the mistake that Ben Franklin uh, unfortunately made. And so the charge is the positive Q on the positive plate. And that's by convention. Okay, now charging and discharging capacitors. Suppose an uncharged capacitor is connected in series with a battery and bulb as shown. Predict the behavior of the bulb when the switch is closed. Well, we've seen this in class, okay? Spoiler alert. Uh, the bulb starts bright, then dims to dark. Okay. Now, set up the circuit and check your prediction. If your prediction is in conflict with your observation, how can you account for your observation? Okay, we'll do that in just a moment. Without using a voltmeter, determine the voltage difference across the capacitor at the following times. Well, just after the switch is closed, the voltage across the capacitor, I can write as the charge stored on the capacitor divided by the capacitance. And if the right after the switch is closed, that capacitor is empty. It takes time to build up the charge on the capacitor. So when I close the switch, right at this time here, the charge is going to build up over time. But if I look right after I close the switch, it's got to be pretty much the same as right before I close the switch, which is 0. And so that means the voltage is going to be 0. And um, and you know, I know the voltage across the capacitor has to be 0 because this bulb is just as bright as a single bulb, a bulb in a single bulb circuit. And so there has to be 0 volts across that. Now, a long time after the switch is closed, the voltage across the capacitor is going to equal the voltage across the battery. And that's because the bulb is dark, and a dark bulb has 0 volts. Okay. We're going to use a voltmeter to check our predictions. Okay, so we go over here to the other camera, and we're going to, uh, let's see here. I'm going to there. I'm going to go there. And okay, now, so here's my battery pack. There's my capacitor. And then I go to the bulb, and closing the switch is when I connect this wire here. And so I'm going to close the switch. If I had measured the voltage there, it would have been 0 right after I closed the switch. You see the bulb is getting dimmer and dimmer and dimmer and dimmer and dimmer and dimmer until it goes out. And once again, we've done these measurements before. The voltage across the capacitor is the same as the voltage across the battery, 2.97. Okay. Um, okay, let's go back to our okay. We have checked our predictions. Suppose that instead of connecting the uncharged capacitor to a single bulb, we connect it to uh, the two bulb circuit shown at the right. Predict how the initial brightness of bulb B compares to the initial brightness of bulb C. Uh, that would be the same with our current model. We know what goes around comes around. In other words, the current has to be the same everywhere in a loop. And so B and C are in series with each other. And so let me turn off my phone. Okay. Um, Predict how the initial brightness of bulb B compares to the initial brightness of bulb A above. Uh, B is dimmer. Essentially, right after we close the switch, um, we we can think of that empty capacitor with 0 volts across it as a wire. And so two bulbs in series are going to have less brightness than a single bulb. They each have half of the voltage of the battery across them, whereas a single bulb has the full voltage of the battery across it. Now we're going to discharge the capacitor and then set up this circuit with the uncharged capacitor and check our predictions. So let's do that. Okay, and so first of all, we have to discharge this capacitor. While we're doing that, I will set up another bulb. Okay, now um, we now have an empty capacitor. Uh, and that goes to the first bulb and then to the second bulb and then back to the battery. I'm going to put um, the leads of this voltmeter across the capacitance. And what we see is that it's almost zero. We didn't quite wait long enough. Okay, there we have it. Now it's empty. Okay, now um, we're predicting that these two bulbs will be dim, but they'll be equally dim, and then they'll go out. And during that process, the voltage across the capacitor should raise up to the voltage across the battery, because the bulbs will be dark then, and there's no voltage across the dark bulb. So let's go ahead and do that. And sure enough, um, whoa, okay. I picked the wrong bulb. That one's burned out. Okay. Guess I should have checked that beforehand. Let's try it again with a bulb that is not out. Okay, we've got the capacitor empty, and now we go, okay, those two bulbs are equally dim, equally dim, and they're going out, and going out. And you see the voltage across the capacitor is quickly going up to the voltage across the battery. And sure enough, we're almost there. And there we go. Okay. Well, that worked. Okay. So predict how the final charge on the capacitor compares to the final charge on the capacitor from part A? Well, the charge is equal to the capacitance times the voltage. Um, it's the same capacitor with the same capacitance. And we found that in both cases, the capacitor ended up with 3 volts. And so that was the same. And so it's going to be the same. Now, suppose instead that the bulbs were connected in parallel rather than in series. Predict how the brightness, the initial brightness of bulb D compares to the initial brightness of bulb E. Well, they have to be the same. Again, if I think of that empty capacitor as a wire, we've seen that circuit before. We know that each of these bulbs is just as bright as a single bulb uh, circuit. So uh, D is going to be equal to A, and it's going to be brighter than B, which is equal to C, because these are in series, and these are acting like single bulb circuits. Predict how the final charge on the capacitor compares to the final charge on the capacitor from part A. Well, again, once these go dark, there's 0 volts across them. Any path from one side of the battery to the other has to have the same drop that we have rise over the battery. And so that means it's going to be the same, uh, equal to the battery voltage. Okay, set up the circuit and check your predictions. Let's go back. Okay, so again, what we want to do is we want to discharge uh, that capacitor, and then we're going to set up a okay, so we've got that, and now we're going to set these up in parallel. Oh, no, I'm sorry. I need to disconnect that. So, ah, ha, ha, ha. Let me empty the capacitor again. Okay. Now we'll set up our parallel network. And you can see that these two bulbs are parallel because they're connected with wire on both sides. And this side is connected to the negative terminal of the battery. And so we're going to connect this side to the capacitor. And we're going to, first of all, disconnect that because we want to watch what happens to the voltage across the capacitor during this whole process. Okay, so that's not the one I wanted. This is the one I knew in the pre-existence. Okay, so when I close this switch, the reading across this capacitor should be 0, and these two bulbs should each be as bright as a single bulb circuit. And 1, 2, 3, whoop, they're bright. They're both bright. And now they're dimming. And looky here, that voltage across the capacitor is going up to the battery voltage like gangbusters. It's done. Whereas when we had the two bulbs in series, it took a long time. It was just poking and poking and poking. It just zipped right along, zipped right along. That's important, folks. Hold on to that thought. Okay. Now, we checked our predictions. Now, student one and student two. The capacitor with two bulbs in series got charged up a lot more than the capacitor with two bulbs connected in parallel because the series circuit charged the capacitor for a longer period of time. Well, we know that that's not true because the voltage across the capacitor ended up to be the voltage across the battery in both experiments, both times. And that means that the charge, um, the charge depends on the voltage across the capacitor. And so if that's going to be the same, then the charge is going to be the same. So student two says, I disagree. Well, it's good to disagree with student one. That's been something we can always depend on. The bulbs in the parallel circuit were bright, so this capacitor gained more charge. Again, no, the same amount of charge. Uh, we agree with neither student. Okay, the charge is the same. Now, how do we account for that? Well, with two bulbs in series, the with two bulbs in series, the initial current through the bulbs is small. There's only a little bit of charge going around this circuit each second because of the bigger resistance. On the other hand, when I have two bulbs in parallel, that's a very small resistance. This would be a big resistance and a small current. This would be a little resistance with a big current. And so essentially, we start out with a lot more flow when we have two bulbs in parallel. And that's how I get this capacitor charged up more quickly. Okay. Now, suppose that a different capacitor of smaller capacitance were connected to the battery and a single bulb in series. Predict how the initial potent voltage difference across the bulb compares to the initial voltage difference across the bulb in part A. Well, an empty capacitor acts like a wire regardless of its capacitance. The voltage difference across a capacitor is equal to the charge divided by the capacitance, regardless of what that is. If this is zero, it's going to have 0 volts across it. And that means all of the voltage of the battery is going to be across the bulb. And so the initial brightness of the bulb is going to be the same as with the other capacitor. And what about the final amount of charge on the capacitor? Well, the amount of charge on the capacitor depends on the capacitance times the voltage across the capacitor. Well, this is going to be the same 3 volts when we finally make that bulb go dark. But now if this is smaller, I'm going to have less charge stored. And that should just make sense. Capacitance is how much charge you can store for each 1 volt. Well, if I can't store as much charge for 1 volt, I'm not going to be able to store as much charge for 3 volts. And so the charge is going to be less. And so if we set up the circuit and check our predictions, um, we're going to find that the voltage is going to be the same, and hence the charge is going to be less. I'm not even going to set that one up. I don't think that's worth our time. Okay, now things get tricky. Now we're going to put that bulb in between two capacitors as shown. And suppose that C1 is less than C2. Now I have a second capacitor. This one has 1 farad, and the other one has 1.5 farads. And so those will be our two capacitors. And so let's listen to this argument by the student. Current flows from the positive side of the battery to the negative side of the battery. Since the bulb is isolated from the battery on both sides by the capacitors, the bulb will not light. Well, again, I want you to think about what you think about that statement. I know the answer, and so I'm not going to spend much time puzzling over it. But what the battery does is it steals an electron from this plate, uh, sending it that way. That is going to leave a positive behind, and that positive is going to attract a negative from that plate, leaving a positive here. And um, as I keep doing that, as I keep stealing electrons, this plate gets charged up positive, this plate gets charged up negative, this one gets charged up negative, and this one positive. Now, what's important to note is that for every 1 electron that I steal from this plate, I deliver 1 electron onto that plate. And so that means the Q on 1 has to equal the Q on 2. Okay, let us check our prediction. Um, and then we've got to make some more predictions. Okay, now the first thing we're going to do is we're going to uh, discharge both of the capacitors, and I'm going to do that with this single bulb. Okay, and once we get that one discharged, okay, it's almost there. Close enough. Okay, now we're going to discharge this capacitor. And it looks like it's already discharged. Oops. Yep. Okay. So now we've got our capacitors discharged. In the picture, we had uh, the smaller capacitance was C1, and it was up here relative to the battery. And so we're going to go from here to here to this is the side that's got to go there, because it's got to be, this has to be to the negative terminal of the battery. And so I am going to close my switch and see whether this bulb lights up or not. And let me move it so that you can see the bulb. 1, 2, 3. Oh, it's bright. It's bright. And now it's going dim, 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 dim. Okay, so our prediction came true. Uh, we disagree and we checked our prediction. Okay, last page. Make the following predictions on the basis of your observation of this circuit. Do not use a voltmeter. Just after the switch is closed, what is the voltage difference across the bulb? Well, right after the switch is closed, the voltage difference across the bulb is equal to the voltage difference across the battery, which we found was about 3 volts. What is the voltage difference across each of the capacitors? Well, we know that it's going to be the charge divided by the capacitance, and in both cases, they were empty. And so that's going to be 0. Both of them are acting like wires. Now, a long time after the switch is closed, what's the voltage difference across the bulb? Well, the voltage difference across the bulb will now be 0. It's dark. Now, again, when I said voltage here, I meant voltage difference. I was just getting sloppy there. What is the sum of the voltage differences across the two capacitors? Well, the voltage difference across capacitor 1 plus the voltage difference across the capacitor 2 has to add up to the voltage difference across the battery, which is around 3 volts. Is the final charge on capacitor 1 greater than, less than, or equal to the final charge on capacitor 2? Well, we already argued that it's got to be equal to, okay, equal to, because the electrons are stolen from one and placed on the other. Now, what about the voltage difference across capacitor 1? And remember, capacitor 1 had the little capacitance, and capacitor 2 had the bigger capacitance. Okay? Well, if they have to have the same charge, and so if I look at the voltage difference, that's going to be the charge, and that's going to be the same, and divided by C. And so the smaller capacitance will have the larger voltage across it. If I make the basement smaller, the other side gets bigger. Okay, I can write this again. If I make the basement smaller, that's going to make my voltage bigger. So let's go one last time and check our prediction. If I measure the voltage across the big capacitance, what I get is only 1.4 volts. But if I measure it across the small capacitance, I get 1.6 volts. And sure enough, we get more volts across the smaller capacitance. Okay, that is the end of the tutorial. I hope that this was helpful and that it will give you what you need as you solve your uh, homework. We will stop recording.